So here we're going to take an initial look at combining symmetry elements and some of the limitations in the symmetry elements. So let's start by writing out what we've seen so far. We have a center of symmetry or an inversion point, which we refer to as I. We have reflection symmetry, or otherwise notated as M, or mirror plane. And then we have 1, 2, 3, 4, and 6-fold rotation. Although the 1 is a trivial case because it doesn't really do anything. And then we have the bar 1, bar 2, bar 3, bar 4, and bar 6 symmetry elements. And so here we're combining rotation with an inversion point I. Well, we could do other kinds of inversions, but before looking at those, let's look at some of the limitations. There's no 5-fold rotation. So why is 5-fold rotation absent? So why is that non-existent? This very nice diagram by Klein and Dutro illustrates the case. Here over on the right, we have hexagons, things with 6-fold symmetry. You can think of a 6-fold symmetry coming out in and out of the plane of the board, right here through that red dot. And that gives us a nice clean structure that's very stable. On the other hand, if we have 5-fold symmetry here, right, then we would get a structure that once we start packing it together, we get these large gaps. So the structure would be unstable. There are other kinds of things that we don't see that would just simply be a repeat of other things. So for example, we have looked at the rotoinversion bar 1. The bar 1 is the same as I. So if you write this instruction set, it's the same as this instruction set. So there are repeats. Another repeat that we saw earlier is that a bar 2 is the same as our mirror plane. So this fellow here, that instruction set is the same as this one over here. If you give somebody the instruction to use an M operation, it's the same as using a bar 2. So there are repeats, and then there are things that are simply impossible. Let's take a look at a couple of possible combinations, just as examples. We can take the 2-fold rotational axis, and we can combine it in a case where we have 2-fold rotational axes that intersect with one another in 3 dimensions. So we could have a vertical 2-fold rotational axis here, and this symbol here is a very common symbol to illustrate 2-fold rotation, an ellipse with 2 sharp ends, more or less. So there's one there, and another one there, and another one over here. And so the way we would write that would be as 2, 2, 2. So there are other possible combinations. We could, instead of having a 2-fold rotational axis here, we could make that into a box, and that would indicate a 4-fold rotation, and a 2-fold, and a 2-fold, and that would be a 4, 2, 2. Now, can we make this combination with any set of axes? If we have a 4-fold here, could we make this one a 4 and this one a 4? Could we have a 4, 4, 4? Is that a possible set? Well, it ends up there's a very simple equation that uses so-called spherical geometry, geometry on a sphere instead of plane geometry, like Euclidean geometry, and we can develop this idea here, where we have 1 over x plus 1 over y plus 1 over z in the limiting case that sum must be between 1 and 3. So x could be, and it doesn't matter how we take it, x could be the one in front here. We can let the left to right be y, and then we can let the vertical be z. Any trio that satisfies this relationship here, which comes out of spherical geometry, would be a compatible trio. So let's erase the chalkboard and take a couple of examples. So do we have a compatible trio in the case of 4, 4, 4? Well, this would be our x, y, and z. It doesn't matter what order we take them. So does it satisfy the relationship of this? Is the sum of those fractions something greater than 1 and less than 3? Well, 1/4 plus 1/4 plus 1/4 is 0.75. And so that is less than 1. So this is not a compatible trio. It is not possible. Let's try the case of 4, 2, 2. We would have 1 over x plus 1 over y plus 1 over z, where this x is 4. And again, it doesn't matter what order we take them. This is 2, this is 2. So if we have 1 over 4 plus 1/2 plus 1/2, then we would get the sum of 1.25. And then that works. That satisfies this inequality. It is greater than 1. It is less than 3. So this is a compatible trio. Let's try one last one before we go. 6, 2, 2. If we have 1 over 6 plus 1 over 2 plus 1 over 2, is that sum greater than 1 and less than 3? Well, it comes out to a value of about 1.167. It is greater than 1. It is less than 3. So this is also a compatible trio. We can have a 6-fold rotational axis here, perpendicular to two 2-fold rotational axes that would be perpendicular to it. How about the case of a 6, 6, 6? Would that be possible? If we take that sum, 1 over 6 plus 1 over 6 and 1 over 6, we'd find out that it's less than 1, so that would not be possible. So coming back to our introduction to combinations, we have limits. We can only make so many different kinds of things. So we can have a 2, 2, 2, we can have a 4, 2, 2, we can have a 6, 2, 2, but we can't have a 6, 4, 4. We can't have a 4, 4, 4. So many of these are just simply geometrically not allowable. And that will limit the total number of ways that we can arrange atoms or atomic clusters in 3 dimensions, either because in the first case we have structures like that 5-fold symmetry that are not structurally stable, or we have things like this that are simply not geometrically possible.